to class. Okay, so in class we looked at a problem where we had what we call a semi-infinite rod, where we have one end, but the other end is infinitely far away. Instead of going infinitely far in both directions, just in one. And so now we're going to look at a finite rod with a length L, and say it has a charge density, say 2 microcoulombs per centimeter, and we want to find the electric field at 2 points. Point A, which is kind of what we did last time, it's perpendicular to the left end of the bar and just a certain distance away. We found for a semi-infinite rod the interesting result that the x and y components were equal. And so the electric field made a 45-degree angle, and that was true, wherever h was, no matter how close or how far away. So, an interesting result. But now we want to look at, just a finite rod, so essentially the same problem, except for the length. And I also want to look at point B, which is going to be just like along the rod, but a little bit past the end. So a distance d. Let's make up numbers for this. Let's say h equals 6 centimeters, d equals 4 centimeters. Let's say L is 100 centimeters, just like 1 meter. So we have like a meter stick that is uniformly charged. And I'm going to put a problem similar to this on the homework, just a little heads up, where we're going to look at point B, but this will be a homework problem. So you want to find the electric field at point B, except in the homework problem, the charge is not going to be uniform. It's going to start out with like a certain charge at the left end, and that charge is going to decrease to 0 by the time it reaches the right end. But pay attention to what we're doing when we find the electric field at point B. It's essentially the same. But let's start out with the harder problem, finding the electric field at point A. So we have an element of charge dq. That's a distance x from the left end. And so the distance from that charge element to the point A is r. And let's draw the electric field here. And that is dE. So that's the electric field just to that charge dq. And then we're going to integrate from x equals 0 to x equals L. So let's start out by looking at the magnitude of dE. We'll define that angle as theta. So dE, that would be KE dq over r squared. And dq, that's lambda dx. So it's a linear charge, or I call it lambda not because we can just call it lambda. And the homework problem, that's going to be a variable lambda, so that's just going to be the constant value, and then it's going to be multiplied by another factor that will bring it to 0. But let's just call it lambda. So, and again, this is the magnitude of the electric field. And we want to find its components. So actually, just to save space, what I'm going to do is say dEx. This is dE, and then we have cosine of theta. And dEy, we have the magnitude, Ke dq over r squared, times sine of theta. Now, if I'm looking at this triangle, we can say that cosine of theta is x over r. And sine of theta is h over r. And one more thing, let's replace dq with lambda dx. So again, instead of just writing this all out, kind of erasing it just to try to, you know what, let's, yeah, because we have another change to make. We kind of start over almost. We have dE. Let's just work it out here and then erase it. So that would be KE dq over r squared. And so then dEx now dq is lambda dx. So that's the magnitude of the electric field. And then we multiply by cosine of theta, which is x over r. And similarly, dEy, that would be the magnitude times sine of theta, which is h over r. Now, from this triangle, we can see that x squared plus h squared equals r squared. Or r is x squared plus h squared to the 1/2 power. So let's simplify this as much as we can. So we have ke lambda, and then we have x dx over r cubed. So that would be x squared plus h squared to the 3/2. And for the y component, we have ke lambda h times dx over x squared plus h squared to the 3/2 power. So yeah, same r cubed on the bottom. And so now let's write our final results up here. And then I'll erase the bottom. Okay, so dEx, we have ke times lambda. And then x dx and then here we have ke lambda h times just dx over x squared plus h squared to the 3/2. Now again, this is exactly what we did last time in class. The only difference, so this is just the element due to this charge, and again, this is literally the exact same thing we did last time. But now to get the total electric field, we have to integrate over the entire charge. And so in this case, you know, last time we integrated from 0 to infinity. Here we're going to stop at L. So everything we've done is exactly the same as what we did in class. And now we're going to integrate. So I think we'll just do dEx, write down the result, and then we will erase it to make room for dEy. So let's see. I wonder if we want to do ke lambda. We're going to have that term in both. Let's just get a number for that. Actually, let's do it here. So ke, that's our electric constant, 9 times 10 to the 9th Newton meters squared per coulomb squared. And then lambda is 2 microcoulombs per centimeter. So let's convert this to basic SI units. 100 centimeters is a meter, and 10 to the 6 microcoulombs is 1 coulomb. So this is going to be an easy calculation actually. We have 18, so just 9 times 2. We took care of those. Here we have 10 to the 9, 10 to the 11 divided by 10 to the 6. So that's times 10 to the 5th. So we took care of that, and that, and that. Microcoulombs are going to cancel. One of the coulombs is going to cancel, and centimeters, and one of the meters. So we have Newton meters per coulomb. And we can write this in scientific notation. Let's do that. We have 1.8 times 10 to the 6 Newton meters per coulomb. Okay, so yeah, because we have that in both terms, so let's do that off to the side. And now let's look at these integrals. So EX is just going to be the integral of dEx. And so we have this ke lambda. It'll be shorter just to write it out instead of putting in the number. But now we have the integral from x equals 0 to L of x dx over x squared plus h squared to the 3/2. And we're integrating over x here. So we can make a simple U-substitution. If we let u equal x squared plus h squared, then du is going to be 2x dx. And so yeah, let's do that. So u is equal to x squared plus h squared. Du is 2x dx. And now for the limits. When we plug in, we're integrating over x starting at 0. So let's call this ul and uh. So like this is our lower limit, this is our upper. And so ul would be, that's what we get when x is 0. So that would be h squared. And that's when x equals L. So that would be L squared plus h squared. So now let's make our substitution. So x dx, that is 1/2 du. So we can bring the 1/2 in front. And again, we can just put our limits, ul and uh. So x dx, that's du over 2. We already took care of that, so we have du. And then on the bottom, we have u to the 3/2. So we can say this is u to the minus 3/2. And again, this is just a standard integral then. Just like the integral of x to the n, as long as n doesn't equal -1, we're fine. So we have to just add 1. So we have u to the minus 1/2 divided by minus 1/2. So let's do this. We have ke lambda over 2. And then so like lower and higher value, whatever we call those. So again, this is, yeah, let's see. Let's do it off this side. We have u to the minus 1/2 divided by minus 1/2. And so, yeah, if we multiply by -2 over -2, we have -2 u to the minus 1/2. And then -2 and -1/2 is just 1. U to the minus 1/2 is 1 over the square root of u. So there we go. And now let's, these 2's cancel out. And so we have so we start with, the 2's cancel out, so we have minus 1 over the square root of mu h, so I put that here, and then minus, negative 1 over the square root of ul, and so it's, the two negatives cancel out. And we might want to just leave it in this form. Let's do this. We have ke lambda 1 over the square root, the square root of ul is just h, and then minus okay, and so I guess that'll be our final form for the x component. Now let's compare to what we had in class yesterday. In class yesterday, we were calling this D, but I chose to call that point D. But here, so before we just had ke lambda over D, which is just this first term. And again, if we set L equal to infinity, this term would disappear. Like if L is really big, then we're dividing by a very large number. So the bigger L is, the less significant this second term will be. So if we can, this is consistent with what we did yesterday. If we just had L equals infinity, we get the exact same answer we had last time. But I think we'll just write down this result. So EX okay, and we can figure out the number later, but for now, let's look at EY. So I'm going to erase all of this. And then after we find the Y component, we'll have the electric field at point A, then we'll look at the electric field at point B next. So for y, we have dEy, the integral of dEy. And again, this is a constant. So we have the integral from 0 to L now, just like before, we can't make a U-substitution here. So we're going to have to make a different substitution. And we're going to say that x equals h tangent of theta, and that means that dx is h secant squared theta d theta. And just like before, we're going to call it, once we switch to our new variable, we're going to have different limits. So let's call those like L and H for low and high, or we could call L and U for lower and upper. That would probably be better. But now we're going to be integrating over d theta. So let's do this. Let's say UL. That's what we get when, from the lower limit is x equals 0. And if x equals 0, theta equals 0. So that one's easy. But now the upper limit, well, I don't want to call it UU. That just looks funny. So we'll call it H for high. So again, that's what we get when x is equal to L. Then theta is, so here, let's write this out. So if x is equal to L, we have L equals H times the tangent. Sorry, I was calling these, here, we've got theta lower and theta upper. Let's do that. calling it U because I was thinking of a U-substitution, but yeah, so we plug in x equals 0, and then theta L is 0. Tangent of 0, 0. In this case, when at the upper limit, x is L, so we have L is equal to h times tangent of theta U. And so theta U is the inverse tangent of L over h. And that's why I'm defining these terms instead of just writing the, like before in the last problem, we could have just wrote the, whatever they were, the lower and upper limits. But in this case, I don't want to write an integral and then have inverse tangent of L over h. So we can just call it theta U for the, theta at the upper limit. So let's now make our change of variables. So we have this ke lambda h, and then dx is h secant squared theta d theta. And on the bottom, again, we'll work this off to the side just because we have limited room here. X squared plus h squared to the 3/2. We'll do the whole thing. That would be h squared tangent squared theta plus h squared to the 3/2. And now we can factor the h squared out. And if we factor h squared out, then we have tangent squared theta plus 1, which is secant squared theta. And we can write this as h secant of theta squared, and then raise it to the 3/2 power. So on the bottom we have h secant theta cubed. And then the lower limit's 0, so we can just put 0, but the upper is, I don't want to write the inverse tangent there, so we'll just call that theta u. So again, the bottom we have x squared plus h squared to 3/2. That's h secant theta squared to the 3/2, or h secant theta cubed. And so, let's simplify that. Here we have h over h cubed, which is 1 over h squared. But that's just a constant, so we can pull that out of the integral. So here, if we pull this h out, we have h squared, and then at the bottom we have h cubed. And then here we have secant squared theta over secant cubed theta. So that's 1 over secant theta, which is cosine of theta. Okay, so I can erase this now. Okay. And now this integral is trivial. It's just sine of theta. So I'm going to do this. So we have integral sine of theta evaluated between 0 and this upper limit. And so we have sine of theta u minus sine of 0, which is 0. So we can just write it that way. Okay. And then we have to find sine of u, like sine of theta, this upper theta. And so let's go back to this here. Let's take the tangent of that. We had this earlier. We had tangent of theta u is L over h. So we have lowercase h. Just that's the way I wrote it there. Okay, so tangent of theta u is L over H. Let's make a triangle. Let's say this is theta u. So if tangent, that would be L over H. That would make the hypotenuse L squared plus H squared, or the square root of that. And so sine of theta u, that would be L over the square root of L squared plus H squared. And so that's it. EY, let's write that here. So we have KE lambda over H and then sine is L over the square root of L squared plus H squared. And so now it's just a matter of plugging in the numbers and getting, the electric field at point A. So I'm going to erase all of this. And we have one common thing here, the square root of L squared plus H squared. So let's do that. We'll kind of do this in pieces and then put them all together. All right, so let's do L squared plus H squared. L is 100 centimeters, so 10 to the 4th, and H is 6. Kind of makes me want to change H to something that's a little more significant, because here we have, this is basically going to be 100. I think I made this point a little too close to the rod. So let me increase that. Let's make it 20 centimeters. I'm okay with D being 4, I think, but yeah, let's just make, we haven't used the number at all. So we're fine changing it. So yeah, let's say H is 20 centimeters. And 20 squared is 400. So here we have 10 to the 4th. And then we add 400. Now we might get somewhere. Well, still going to be fairly close to 100 when we take the square root. But let's see what we get numerically. Yeah, 102. It's 101.98. So let's write this here. So yeah, the square root of L squared plus H squared is 102 centimeters. So it's not much different than L itself. But that's fine. Let's put everything together then. So EX, we have KE lambda, so that's 1.8 times 10 to the 6 Newton meters per coulomb, and then 1 over H, so we have 1 over 20 centimeters, minus 1 over 102 centimeters. And let's put a conversion factor, 100 centimeters per meter. So then we'll just get newtons per coulomb. The centimeters are going to cancel out. That meter will cancel out. We'll get our electric field in newtons per coulomb. And so, let's just do this. 1 over 20 is 0.05. And So this in parentheses is 0.04. So, well, if we multiply by 100, this whole thing is 4. So 1.8 times 4, what's that? 7.2. So the x component of the electric field is 7.2 times 10 to the 6 newtons per coulomb. Okay, now let's find EY. So we have this KE lambda over H. So we have 1.8 times 10 to the 6 Newton times meters. H is 20 centimeters. Well, here, let's just do this. So H is 20 centimeters. And then we have L, which is 100 centimeters. And then that square root on the bottom, we already did that, 102 centimeters. So I just canceled out the centimeters. And then 100 centimeters per meter. So we get newtons per coulomb again. So let's see, 100 divided by 20 is 5. So here we have 1.8 we're going to get seemingly much larger y value by a pretty large margin. I wonder if I did this right. Well, let's see what we get first off. Yeah, so 100 over 20 is 5. So this would be 1.8 times 5. This would be 9. And then we'd have times 10 to the 8th newtons per coulomb, or 900 times 10 to the 6th newtons per coulomb. Oh no, I totally neglected that. Yeah, I was wondering why that other component was so much bigger. So, yeah, essentially this 100 and 102 are going to cancel out. So I think we're going to have about 7.8 times 10 to the 6 newtons per coulomb. For some reason I completely didn't even notice that 102 centimeters in the denominator. So yeah, basically what I did, 100 and 102 cancel out. 100 over 20 is 5. 5 times 1.8. What am I doing? That's 9. So 9 times 10 to the 6. And again, if you don't like this cancellation, let's just say 9 divided by 1.02, 8.8. Okay, we'll do that. Wait, did I do that? Yeah, 8.8 times 10 to the 6 newtons per coulomb for the y component. Okay, so yeah, that's our electric field at point A. We found both components. And yeah, we'll just double check these numbers one more time, and then because I'm about to erase this. Yeah, so I'm getting 7.2 times 10 to the 6, and then yeah, and then 8.8 times 10 to the 6. Okay, so that's the electric field. And again, it wasn't really much different than we did with the semi-infinite rod. But, yeah, we just had to, stop it at x equals L. So the only difference were the limits of integration. I think it works out a little easier if that upper limit is infinity. But, yeah, not too much different. But now let's look at point B. Let's look at the electric field at point B. So I'm going to erase all of this. And now the R that we have here is, the R in the formula is a distance from the charge to the point where we're evaluating the electric field. So we don't need this for this one-dimensional problem. So let's say we start here. So from here to here is x. So like this distance is x, this distance is r. So we have x plus r equals L plus D, because this point, the x-coordinate of point B is L plus D. We go from the end of the rod plus a difference D. And so we can see that x is L plus D over R. R is L plus D minus x. That's the one we want. And so let's set up the electric field. We don't need this anymore either. So again, we have our charge here at a location x. So the electric field we get from that, dE. Let's do it here again. And then we'll move it up. That would be KE dQ over R squared. And dQ is lambda dx. And then R squared, that would be L plus D minus x squared. So that's dE. And I think we can just leave it like that. And, well, here, we can take out the constant, but otherwise we'll have to leave it alone. So dE is KE lambda times dx over L plus D minus x, all in parentheses, squared. Let's define L plus D to be like just big D. So we can just simplify this. So we have like big D minus x squared. And so now to find the electric field at point B, we know the electric field due to this little piece of charge. So we just add them up, all these dQs, along the entire length of the bar. So E is integral dE. Integrate from 0 to L. Okay, so that is our electric field, and now we just have to do this integral. So again, this one's a little bit easier because there's no breaking things into components. And yeah, really all we want to do here is make a U-substitution. Because D is a constant. So let's set U equal to D minus X. Then du is equal to minus dx. And x is going to be equal to d minus u. Oh, actually, we don't even need that. Sorry. We don't have an x to plug in anywhere. So, yeah, I was thinking, for some reason I thought we had an x in the numerator, but we don't. So, that'll make things a little bit easier. So, oh, yeah. Okay, a little hint. The reason I was going to solve for x is because in the homework problem I'm going to give, you're going to wind up with an x in the numerator at some point. But we don't need that here. So let's just make this change of variables then. So first off, let's look at the limits. The u lower that's when x equals 0. So if x equals 0, then u lower equals d. And I don't like writing u, so let's call this the higher limit. So the upper limit, that's when x equals L. So that would be d minus L. So let's look at our electric field now with our change of variables. So Ke lambda. Now we integrate from UL to UH, which is d minus L. And dx is minus du. And then we divide by u squared. So what I'm going to do is I'll just do that and then talk about it. So I got rid of the minus sign by just flipping the indices around, because d minus L is a smaller number. So that's actually, let's simplify it a little bit more. But anyway, remember you can multiply an integral by -1 by flipping the two limits. And d minus L is lowercase d. If you just look here, d minus L is lowercase d. And so we could have d, and then this one is L plus d. And then the u squared in the denominator made that u to the -2 du. So now let's do the integral. Let's do that. So the integral of u to the -2 is u to the -1 divided by -1. So u to the -1 is 1 over u, and then we have that -1. So the electric field is going to be Ke lambda. And so we're going to have -1 over L plus d. And then minus -1 over d, so that's going to be like that. All right, so then it's a matter of plugging in the numbers. We have Ke lambda, that was 1.8 times 10 to the 6 Newton times meters per coulomb. And then, we could combine it into one fraction. Let's just say 1 over d is 1 over 4 centimeters. And then minus 1 over 104 centimeters. And let's throw this conversion factor in here. So we'll get units of newtons per coulomb. So I can do this part first. 1 over 4 minus 1 over, let's see. 1 over 104, that's 0.24, and then times 100. So that whole thing here is 24, and then times 1.8. So what I'm getting is 43 times 10 to the 6 newtons per coulomb. That would be the electric field at point B. So 43 times 10 to the 6 newtons per coulomb. All right, and again, pay attention to this last part we did. It'll be very similar to the homework. The only difference is that lambda is not going to be uniform. I'll even tell you what it's going to be. In the homework, lambda is going to be this. So we've got lambda naught times 1 minus x over L. So at x equals 0, we just have lambda equals lambda naught on this end. And then at x equals L, we have 1 minus 1 is 0. So basically the density just drops to 0 at this end. And it's a linear, just a linear drop from, we'll say, 2 microcoulombs per centimeter here, and it's just going to drop linearly down to 0. And so basically you just follow these steps, except instead of lambda being outside of the integral, you're going to plug that in, and and so your integrals will be a little different, but that's basically it. And so I guess we'll stop here, and practice setting up and doing these type of integrals. They're fun. You should enjoy doing this. So I think we'll stop this one here.